Hello everyone, I'm Wish Wu from Trend Micro, Mobile Threat Response Team. Here we will talk about the Perf from profiling to kernel exploiting. Performance counters for Linux are a new kernel-based subsystem that provide a framework for performance analysis. They cover both hardware features and software features. If you run command menu perf event open, they will show more than 1,000 lines descriptions. 1,000 lines on my wide screen. It is very rare to describe only one system call. So it is a very complex module in the kernel. System call perf event open is enabled on the most of the latest smartphones. There is no strong relationship between the Android version and the customized Android Linux version. Vendors can also customize their Linux kernel and the SE Linux policy. Most Android versions from 4.4.4 to 6.0.1 have enabled this syscall. An application which has no Android permission required can invoke this syscall. If you develop an Android application, you should declare you have what the permission you should have. App will, without declare any permission can invoke this system call. They will give a false sense to user to trust the app will not do any dangerous action. Many CPU vendors would like to add their own PMU. PMU is the performance monitor unit. They will implement their own method to monitor their, such as CPU, the performance of CPU and other hardware. For specific performance testing, these codes will not be merged into the main line of Linux. So these codes may not be totally reviewed. Here is the code relationship of Perf. Performance subsystem has many architecture and vendor-related codes. Architecture-specific codes such as ARM and x86 and PowerPC and such as architecture related, and vendor-specific codes such as Qualcomm or Samsung or such vendors. They will add their own codes into the kernel, not in the mainline of Linux. Here are 4 ways for me to detect the bugs in the perf. First, we can use perf. We should thanks to these two guys. They released a paper and a perf further tool. That helps me a lot. They put their projects on the GitHub. And here is their papers. Then the second tool is Trinity. Trinity is a well-known system call further. It sometimes helps me. Then you should code review the Perf subsystem. They have many codes. You should know how it works and their relationships. Then after read the code, I write some tools by myself, test their this code, specific codes in the kernel. I have found 5 bugs in the perf subsystem of Android. The CVE 2016-0805 and the CVE 2016-0843 are out of boundary access bugs in the kernel. It is in the Qualcomm CPU related codes. The performance related codes, performance test codes. I also submit some issue to Google. Google has defined the severity to critical, and another one is low. There is unpublished. They are not published now. Then I will exploit the critical bug, CVE 2016-0819. Before the bug is fixed, these phones may be possibly affected because I haven't tested on all of the phones. I have tested on the Nexus 6 Galaxy, Samsung Galaxy Note 4, Note H. This bug is worked. This bug exists in all Android smartphones, which has Qualcomm CPU and Linux version 3.10 series. Here is a bug-related source code. The red lines are added by Qualcomm or Google. Google variable constraint duplicate is added into function perf release. Perf release is connected to the close system call. If we invoke close on a file description, then we'll invoke the perf's release. Once we invoke close and set the constraint duplicate to 1, then the event state will change from off to active again. In fact, Google or Qualcomm's developers think this variable is used internal, but we can set it in the user space. That is the main reason to cause the bug. If we set the constraint duplicate in the user space and the state will equal active. If it don't equal, it will return. But I will I can set it to active when we close the file disk FD. Then we'll invoke the PMU delete function. That means if we can disable change the active to off twice, then delete the event twice. Here is the test codes. Test. We declare a perf event attribute, then type to trace point. Trace point is 9 point. It is a main point. This variable is not in the standard header file. Is a NTK provided by Google. So we should use a shift to set this bit to 1. Then perf event open. Get a FD. I'll control FD to disable it. Then we'll delete from the list first time. Then I close it. Then we'll delete the perf event from list the second time and free it. The bug can double delete a HList node. But for list in kernel, delete does not equal free. It is not C++. The delete is an operation, is a function to delete node, delete a list of, delete a node from list, not free it. A deleted node can be added into HList again. No nodes can only be added into HList head, but can be deleted from anywhere. This uses the HList. Every node has a next pointer, which points to the next node. They also have a pprev pointer, which points to the previous node. The HList starts from a list head. List head has a first pointer points to the first node. Then the last node, the next pointer points to now. I forgot to write it here. Here is the node delete function of HList. Deleting one node, the pprev point of the node will be set to list pointer 2. List pointer 2. After they delete the node, they will set the pprev pointer to list pointer 2. List pointer 2 equal 200,200 in 62-bit Android. It is a little bit different from the 64-bit Android. Then I use memory map system call and a memory lock system call to put a memory to the address 200,200. I use the map populator parameter to make sure the physical memory is mapped to the virtual address 200,200. If you just use a memory map, the kernel just mark that you have the address. Not means the physical memory is really allocated to your process. They use page fault, the technology, to put memory to you when you use it. In the match security bulletin, Google set the list pointer to 200. Its value is smaller than the memory map minimal address. That means you can't use the system call to put memory to the 200. This address is not allowed. When the value is smaller than memory map minimal address, it mitigates the problem. Here I will demo the double delete operation. It may a little bit confuse you. First, I do IO control. Just IO control will delete the node 20 once. The program will go along node 20's pprev pointer to find node 20's previous node. Now the previous node is node 10. Then modify node 10's next point to point 30. Then the program will go along the next point to find its node 20's next node. Next node now is node 30. It modifies node 30's pprev pointer to node 10. Then init the node 20 pprev to 200. 200. Once delete is finished, then I close node 20. The program will go along the node 20's pprev point to find the memory in 200, then treat the memory in 200 as a node. Then write node 30's address to 200. It leaks the node 30's address to user space. That is an info leak. Then as the program go. After close node 20 is freed now. Then I just close the node 30 directly. Node 30 is gone. Node 10's next point to a freed space. Then use after free is triggered. It is simple, I think. No, because I have many other work to do. We must create a grace period to run at least delete RCU. An easy way to do this is calling sleep. Then the grace period is a term of RCU. RCU means read, copy, update. It is a technology in the kernel. It will delay the delete operation. We should make sure the node is really deleted. We must, the easy way to do this is call sleep. But if we invoke sleep, the node will schedule out the CPU. After schedule out CPU, the node will be deleted. All the node will be deleted from the list. Then the process scheduling the CPU, the node will be added to list again. They will cause some problem, such as the infinity loop. It is a side effect of invoking sleep. And so how will refill the freed node? We should put the data to the address. The last point to the freed address. Then I will try to create this memory layout in the kernel. I open many FDs, FD 0, 1, 2, 6. It is low address to higher address in the kernel. left is low address, right is high address. The memory layout looks like that. The head, the list head is here. Then next. Last one is to now. Then every four objects in one page. But the real situation is complex. The real situation is more complicated. I will try to create this memory layout. But we have another problem. One process only have 1,024 FDS. So I use fork out many child process. Every child process will open many FDs to fill the memory, raise the address up, then create a clean space. We can control the memory space. Now we should thanks to thanks to these three guys. They released a paper and technology to give me a chance to supply my customized data to kernel space and still know where the data is. Simply said, two virtual address possibly mapped to the same physical memory. It is possible. Kernel call the memory here, the kernel space memory here is a low memory. Then user use the high memory. According to the kernel memory reuse rule, I exploit the use after free bug like this. By continuously exposing the next node address until I find a node that at the start of a page. I double delete this. I know this address. If the address is not in a start of a page, then I go to sleep and then recreate the list. Just recreate. Then I double delete this to find its address. It is not in the page of start. Then go to sleep there. Then I double delete it. Then I found the address at a start of a page. Then I delete. I close it. Then close one more page. This operation is used to raise the success rate. Success rate. Then I use the return to direct technology to supply data to this address. Then the last FD, the next pointer is the point to here. Then I put the data to here. The last step, I will command the kernel to traverse the list and use a function pointer that I controlled. This object has a function pointer kernel use the function pointer, after kernel use the function pointer, I can control its PC register. The ARM32 don't have haven't enabled the return to user technology. Return to user technology is the kernel context can be changed to the user space directly. So we can jump to I prepare a piece of code in my user space, then I let the kernel jump to my user space code, then I execute my code. Then the get root operation is very similar to the Gibbons. It is his nickname possible. Tower root source code, but they have some difference. But the first step is same, is set the address limit to the maximum value of the integer. Address limit just as its name. It limits one thread in the kernel which address they can, the maximum number of address they can access. To the if we modify it to the maximum number of integer, we can access all the kernel space. Kernel's virtual address start from C000, start of the C address. We can access the whole virtual address of kernel. Then we can do anything in the kernel, do read, write, and other things. Then we should set it is a variable in the kernel. It's a global variable. Android Linux kernel doesn't have kernel address space layout randomization for now. So it is a fixed address. We can extract it from the image, boot pointer img image. So we know address, and we set to 0 to bypass the SE Linux. If we set the variable to 0, the whole SE Linux is done, is disabled. The previous they will stop you now. Then I modify the structure credential, then SE Linux security object, then set it to 0 or -1 and some value here. After you modify your credentials, then you can be root. Your process change to root now. Now I bring the next 6 here. I will root it now. Use this exploit. We are share user now. We are share. Username is shell. The SE Linux context is share user. Role is shell. Yes, I just say. maybe I show the version of the Android. This is 6.0.1. Sham is its nickname, and it has the February security patch level. Because it is fixed in the match, I submit the issue to the Google. It is not a 100% success rate, so it may fail sometimes. It is here. It is fork out a child process and do some work. Find a target. It is on the page start. This address is on the page start. Then I'll try to supply data. Then it shows the closest address. Then try again. The supply failed. Then try again. The seems failed. Well, restart it. Okay. Please wait a minute. Okay. Yes, thank you. Can ID my ID is root now, and my connects change to the kernel. Sharp here. Can create can try to create a file in the system directory. Touch file. Yeah. Then go to there. Boy, it's so hard to read now. Okay. Huh? Oh, here. Root, right? It's rooted. Now we really have the root permission. Thank you. I finished. Anybody have questions? We can.
I have a mic here if anyone has questions.
You demonstrate on a Nexus.
Yes.
And my question is, this vulnerability is can be used on other devices like Samsung or other vendors, or just on the Nexus, or you didn't check it? I mean, the kernel vulnerability that you exploited right now?
The exploit should work on the first we mentioned.
Generally, how generic is your exploit? This is my question.
Huh? What?
You tested on all those devices?
No, I haven't. Possibly, and the P is possibly effect. I have tested this phone, and here.
Okay, thank you.
But I should mention the bug is the exploit is not working on the ARM64 because it mitigates the problem. Google. Okay. The list poison 2 is the DEAD 000 then 2020 DEAD dead. This address is the dead. The address start with dead is cannot be put memory to itself. It is a kind of design to mitigate these problems. Then Google has set to 200. List delete operation is not working now. It's not working now. Any other questions?
Any more questions? All right, well, warm applause to Wishful, guys.